Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I want to welcome everybody this morning. I'm really impressed at the size of the crowd so early in the morning. I was even more impressed when I walked in here at 8:30 and there was already a lot of you here. It's great. We have a whole set of wonderful visitors on campus, and so really want to take advantage of bringing them into this dark room on this dreary day. And luckily we're not missing the beautiful Seattle sunshine today, so it's a great day to have this symposium. As you can see from the schedule, we built in a lot of time for breaks. So although I'm really looking forward to hearing from all the speakers today, and I think we're going to have a great set of talks, I'm also really looking forward to the break times, not just to drink coffee, but to be able to talk at length with the speakers and with other people. At the end of the first session here at 10 o'clock, I'll talk for a couple seconds how maybe we can leverage that time and make it even more useful. My name is Michael Cohen. I think most of you know me. Rick Zalitsky and I organized the day, and we'll probably tag team being up here to host everybody. But I don't want to take too much time standing up here, and like to welcome our first speaker, which is Hanspeter Pfister, who as of a few days ago, I guess, is now from Harvard University, and is going to talk to us about some recent work. Thanks, Hans.
Great. Thanks, Michael. Welcome, everybody. Thanks to Rick and Michael for organizing this wonderful symposium. I think this is a great opportunity for us to mingle. So this is work with Kalyan Sunkavalli, my PhD student at Harvard now, and Wojtek Matusik. And we did this work while we were still at Merle. Wojtek is now at Adobe Research, and I, as Michael said, moved to Harvard as well. Simon Rysinkevich is our collaborator at Princeton. So I'm sure you all know about time-lapse photography, where you capture images at a certain rate, let's say every 5 minutes, and you play them back at a much faster rate, let's say 30 frames a second. And it actually dates back to the 19th century. But what's interesting today is that there are literally thousands of cameras on the web online that capture typically outdoor scenes such as these, and that people can go to and apparently have pleasure in looking at and maybe checking the weather and the skiing conditions and whatever. So we figured, wow, that's great data, you know, but it's actually quite underused because it's in a form that's really hard to analyze and hard to comprehend, except for maybe a quick viewing pleasure. And part of the problem is the size of the data. If you have uncompressed frames of time-lapse sequence of a day, you end up with about a gigabyte of data. Now, of course, you could video compress that, but that makes it even less useful for, let's say, automatic scene analysis. So what we wanted to do is come up with a representation that is both compact, that is intuitive and meaningful for a human, for a user, and that can be edited. And also we wanted to use then this new representation to do some kind of scene analysis. So if you look at typical outdoor scenes, you see that the image really is comprised of these various components that result from illumination, reflectance, the scene geometry, and shadows. And in our work, we make some strong assumptions. First of all, we only deal with fixed cameras. Secondly, we assume that the scene is mostly static. And that's, of course, practically never true, because as you can see, there is lots of things moving around. And lastly, we're assuming that we have direct sun illumination throughout most of the sequence, so that we have mostly clear skies. Now, even if these assumptions are not 100% true, we still can do a pretty good job, but at some point this algorithm will start to fail. So I'm going to talk a little bit about related work, and then I'll present our factorization for time-lapse video, and finally show you some results and applications. There's been a lot of work on inverse rendering in graphics, where we try to recover rendering parameters from photographs or video. And in particular, there's been really exciting work on using outdoor scenes to do this. However, and typically the goal of this work is to create new images, either under different illumination or from a different point of view. But in all of this work, especially for outdoor scene, people assume that they know the illumination, so they capture the sunlight with a light probe typically, and they all assume that you have a 3D geometry of the scene, either very simply put together with something like the facade system, or maybe more complex. We don't make any of these assumptions. Our work is most closely related to the work in intrinsic images that's been very popular in computer vision, introduced by Barrow and Tenenbaum. It simply says that you can decompose a set of images or even a single image into some fundamental components such as reflectance and illumination. But as you can see in this example here on the right, in the illumination component there is still shadows. So the typical intrinsic image decomposition doesn't go quite far enough, and I think we're pushing the decomposition a little bit further. And finally, there's been recent work in reflectance factorizations in computer graphics. And the goal there is to take some measurements of real-world materials and to decompose those into some measure of a BRDF and some maybe time-varying parameters that then allow you to synthesize new materials. And we're going to use actually a factorization by Jason Lawrence to do our work on time-lapse video. So let me show you the factorization. Let's first look at an example. So here is an image with 3 different pixels, and we're going to plot the pixel intensity as a function of time or as a function of the frame number. So we have those 3 different pixels, and as you see over the course of the day, the intensity at those points in the scene changes. And it's actually quite interesting to see how that changes. So first of all, we observe that whenever the point is in sunlight, the intensity increases quite dramatically. And secondly, we see that whenever the point is in shadow, the intensity is quite low. So we have these illumination changes in the scene. And we can actually use that to analyze the scene. I want to point out that I'm going to show you just one curve in all of these plots, but of course we run our algorithm independently on RG and B. So this is all done on color. So we make 2 observations. The first one is that the pixel intensity really has those 2 components, what we call a sky component when the point is in shadow, and what we call the sun component when the point is in sunlight. And here you see the sky component in green, and here you see the sun component. And the second observation, which is actually more important, is that all of these curves, all of these intensity curves look very similar. And in essence, we can just scale the sky component, so they're all similar up to a scale factor, and we can also scale the sun component. So there is a similarity there, just up to a scale factor. But the sun component also has this shift, and it's an offset based on mostly where the point is located in the scene. And if we can recover this offset, it will give us a strong indication of the surface orientation of that point. So what we'll end up getting in our factorization is actually something like a pseudo-normal map of the scene. So I'll give you a quick overview of what we're going to do. So we have this time-lapse sequence. We can look at it as a spatio-temporal volume, shown here as a little cube. And the first thing we do is we estimate the shadows in the scene using a very simple technique that I'll show you next. And so we end up with a shadow volume, which each frame just shows you where the shadows are with black and where sunlight is with white. So we can then look at only the points where we have a pixel in shadow. In other words, whenever we have a 0 in the shadow volume, we're going to look at the color of that point. And that's the video you see here. Now notice that in that video there is a lot of noise because clearly our shadow estimation is quite noisy, and so you end up with a lot of missing data essentially. But you can also see that we do get colors of whenever points are in shadow. So we call this the sky volume, so it has only the sky component, and we can factor that using a factorization technique that I'll show you later into 2 fundamental components. One is an image, which we call the sky weight image. It's a single image for the whole sequence that relates to surface albedo under the sky illumination. And the other one is a single temporal curve that tells you how the illumination or the color of the sky changes over time. So once we have that, we can actually reconstruct a new skylight sequence. And I'd like to point out in this new sequence, all the missing data has been filled in, because we might have, missing pixels at some frame, but we have pixels from the neighboring frames. And after the reconstruction from our factorization, those are simply being filled in. So once we have this reconstructed sky video, we can subtract that simply from the original video to end up with what we call the sunlight video. So in this sunlight video, we have the scene under basically sunlight, direct sunlight illumination. Now, of course, it's both sunlight and skylight, so it actually is an addition of those two components. So with the sun component, we can do a very similar factorization. And we end up with one single image that has a weight for each pixel describing, again, something related to surface albedo. And then we also have this sun curve that again describes how that color changes over the period of the day. And in addition, we have now something called a shift map that basically explains how these intensities are shifted. And it's again a single image for the whole scene. And as you can already see in this image here, it really relates to surface normals. And it basically says that points on different surface orientations have basically see the sunlight at different points in time. So that's our fundamental decomposition. We take the time-lapse video and break it up into a sum of the skylight video plus the shadow volume multiplied with the sunlight video. And that's fundamentally it. But the whole representation that we end up with really has just 3 images, 2 one-dimensional curves, and 1 shadow volume that describes the shadows. So let me talk about some individual steps here in more detail. First, the shadow estimation. So we do the very simplest thing that one can think of. If you look at these curves and I tell you, well, we need to have these components that are at the minimum of the curves, you can just apply a simple threshold. And that's what we do. Now, I know there are more sophisticated shadow estimation techniques, and those could be applied. But it turns out even this very, very simple technique works in our application. So here is the shadow volume we end up with. Up on the upper half here you see the original sequence. On the lower half you see the shadow video. And as you can see, it's quite noisy. And that's okay, because we can actually deal with the presence of noise in our factorization. So again, white pixels are pixels in sunlight, dark pixels or 0 are pixels in shadow. Now we can actually filter this volume using a spatio-temporal bilateral filter, one of Fredo's favorites, and make it a little bit smoother, and then we end up not just with binary values but with values between 0 and 1. And that would be okay too. We can use that in our factorization as well. I want to point out the flag. You see the flag moving in the upper sequence. So as I said, we're not really dealing with motion. But as you can see, the flag actually shows up in the shadow volume. And it's going to create some artifacts in our reconstruction, which will appear as if we had captured the motion of the flag. But it's simply an artifact of the way we do the shadow estimation. So let's talk about the factorizations. So we start with time-lapse data, which is basically just a sequence of frames over time. And we stick them in a big matrix. So we take each image and we make a column out of it. And we stick that just consecutively into this matrix such that the pixel values go in the columns and time goes along the rows. So that's our time-lapse matrix. And we want to decompose that into 2 new matrices. One matrix that corresponds to pixel weights, those intrinsic images that tell you something about albedo, and one matrix that tells you how that changes over time. And we call that the temporal basis curves. Now there's various techniques to do these kind of factorizations. And there's also various ways you can do the factorization. So I'm showing you here, you could actually say that you want to decompose this one matrix into k different images and k different temporal curves. In our case, we actually choose k equals 1. So we only wanted to do one image and one temporal curve. And we can discuss actually what the implication of that is later. So the decomposition that we use is one that we actually used in previous work. We call it alternating constraint least squares. And we like it because it is a framework that allows you to add constraints on top of this factorization. And there are some really important constraints that we want to observe. The most important one is non-negativity. None of the values in this new decomposition in both of these matrices should be negative. The second one is smoothness. We want to preserve some smoothness because we know that the sun illumination doesn't change rapidly. And again, that might be violated in the presence of clouds and things like that. But under the clear sky assumption, that is true. And lastly, maybe most importantly, we have a notion of a confidence matrix. So in the factorization, we can add a matrix that tells you something about how confident are we about the value at this pixel. So it really gives you a measure of the influence of the data point on the factorization. Now I should tell you that this factorization was put together by people at Columbia, and Jason Lawrence actually puts up the source code for it on his website. And it's based on work he did for the SIGGRAPH 2005 paper. So coming back to this confidence matrix, here we see the time-lapse video, and here is basically the inverse of this shadow volume that we computed. Now, if we take this particular video, we make a matrix out of it again, and we use that as the confidence matrix. It's basically saying points that are in sunlight, or in this case actually under the sky illumination, have high confidence, right? So that's a value of 1. And points that are in sunlight, in this case the points that are 0, have low confidence. And again, we can actually have confidence values between 0 and 1, and so hence we could actually work with a filtered shadow volume. So using that confidence matrix, we can then do the factorization. So if we use the inverse of the shadow volume as the confidence matrix, that gives us this factorization for the skylight. We can then use that to reconstruct the skylight video, subtract that from the original video, and then do the sunlight factorization. Note that if we had used the shadow volume as the confidence, then we would get the factorization of the sky plus sun component. So that's an alternative. So here again are these pixel intensity curves, and we want to decompose them into those two components, the weights and those temporal curves. So again, we do this shadow estimation. We end up with the green parts of the curve, and essentially the confidence matrix tells us that all of the red pieces are missing data. And remember, when we looked at that original video of the skylight video, we had a lot of noise because of the missing pixels. But that's okay, because we can deal with that in this confidence matrix. So finally, when we do the factorization, we end up with this sky curve and with these weights. And as you can see on the left, the sky curve is the same for the whole sequence, for all the pixels. And the weights basically tell you how to scale that curve at each pixel. And as you can see, it basically fits pretty well to that lower part of those intensity profiles. So the sky weights really relate to two things. One is surface texture, of course, because you see that the color basically as if the scene were under just skylight with no sun illumination. And secondly, it relates to a concept called ambient occlusion that tells you how much of the sky are you actually seeing at that point. And both of those are related loosely to the concept called albedo. Yeah?
The bottom curve, can you sort of explain the discrepancy on the right-hand side?
You mean the dip on the right?
Yeah.
Yeah, so that's actually due to the sun setting, right? So it basically tells you that the color of the sky changes when the sun is setting. And yes, it's maybe not a perfect fit. But remember, we end up, actually, this is only one component. This is only the sky component. We're going to add on to that the sunlight component. So the addition of both of these is going to actually make up the difference at the end.
Do you have one of those curves for each color channel, or just
yes, one for each color channel. Now we can do the same thing for the sunlight. Again, remember we had already the skylight factorization, and we reconstruct a full sequence from it, so we have no more missing pixels. We subtract that from the original, so here is the subtraction. Again, we just basically move all the intensity profiles down by that amount. And now we can do the sunlight factorization. So we go again back to the shadow volume. We use the shadow volume itself as the confidence, and we end up with the green parts of the curve. Now these other parts are missing, but that's okay, because again, that's part of the confidence matrix. And so we end up with a sunlight curve and weights, which basically tell you how to scale that single curve for each of the pixels in the scene. And in addition, we end up with this shift map that tells you for each pixel how much you have to shift the sunlight curve. And it basically tells you at which point this particular scene point has seen the sun, at which point in time. And as I said before, this really relates to this notion of pseudo-normals. Now, of course, it's only in one dimension, right? Because the sun has a one-dimensional arc over the sky, so we really don't get 2D normals out of this. But just looking at this image, you can imagine that you could actually do some kind of reconstruction. Now, this is even more interesting if you do it for two different sequences that were taken at different times throughout the year, so that you do end up, the sun moves, of course, so you do end up with two different components for the normal, and then you could actually really do a pretty nice reconstruction.
But if you look at the windows, clearly it's more than, right, the windows
yes.
have the same normals, and that surface.
Yeah, so the windows technically should have the exact same normal as the surface outside. You're right, so it's more than that. And that actually has to do also a little bit with the specularity of the windows. So again, this is the final decomposition. This skylight video, the shadow video, and multiplied with the sun video. But fundamentally the representation is really just a sky image, a sun image, and a shift map image. So 3 images, then those 2 one-dimensional temporal curves, plus the shadow volume. So let me show you some results and applications. The first thing I should show is reconstruction. So we can reconstruct the original sequence from this decomposition. And as you can see, it's doing a pretty good job. You are noticing there is motion in that reconstructed video, even though there is no notion of motion in our decomposition. And that has to do with the noise that was present in those shadow volumes. So you can see, the smoke moving a bit and the flags. But there are people moving on the roofs that are disappearing, and the moving trees are definitely not moving as much. So we're losing the motion in the scene. But overall, it's a pretty good reconstruction. Here is a comparison to a PCA reconstruction. And as you know, PCA is optimal in the least square sense. So we basically did the PCA decomposition that gave us the same RMS error in the reconstruction. And that turns out to be a 5 terms plus mean PCA decomposition. And as you can see, even though the error is actually the same, the shadows in the PCA decomposition are way too smooth. So it's really not doing a good job at capturing that. What's probably more important is a PCA is a really non-intuitive decomposition. You end up with both positive and negative values. And so there is no way that you can actually make sense of that, whereas our decomposition does make sense and is intuitive for a user and can be edited. Here is an interesting video of the residue. So the upper video is our reconstruction. The lower video is the difference to the original. And you can see the lower video basically shows you all the motion. So we think this might be actually really interesting for surveillance or if you want to do tracking. Here are some numbers. The original file sizes you see are several hundreds megabytes, and that's uncompressed, just raw image data. And if you do a PCA, you end up with the optimal compression, of course. But in our case, even with the shadow volume, we come very close to that. So we end up with like 1 to 3 megabytes of data for a whole day of time-lapse video. And if you don't need the shadows, you end actually up with just the 3 images and the 2 curves. And that's much, much smaller, of course. So that's the second column from the right. So here is reconstruction without shadows. And it's actually kind of nice to see just the sequence as if there were no shadows at all in the scene. We can edit the video. So here is just the sun component. This is basically removing all the scattering of light in the sky. So it's like, you're placing the city on the moon or something. We can do relighting. So here we had a sequence where we took 2 time-lapse videos, one in January, one in December, at very different times of the year. So we had 2 decompositions, and then we basically have 2 suns. We can color one of them blue, the other one red, and we can basically replay a relighted video. Here is an editing, so we can edit all of the components of our video and produce a new time-lapse sequence. By editing the shift maps and the shadows, we can emboss logos into the scene. So it looks like there is a SIGGRAPH logo in the snow in the front. And also notice that we removed the shadows from that particular part of the scene. Here is a bunch of other edits. You see we put the SIGGRAPH logo on the building. Notice that even though the logo is there, when the shadows move in, the logo appears to be in shadow. So this would be hard to do. And then we changed the reflectance on the buildings and on the roof. And we also added 3 new windows in one of the images. And just by editing single images, we can reconstruct a full sequence of video. So it's really easy to do that. I should point out that we are not artists. So we could definitely benefit from better taste, I guess. We can do some nice non-photorealistic rendering. The nice thing about this is by just using NPR on the single images, we can get a nicely temporal smooth video that shows the NPR sequence. So in conclusion, I've shown you a decomposition of time-lapse video that is very compact, and it's intuitive, and it's easy to edit. And it actually tells you something about the scene. So it's analyzing the scene into the components that relate to skylight and components that relate to sunlight. And it also gives you an indication of the surface structure or of the structure of the scene. There is a lot more work we can do. First of all, we'd like to deal with more general illumination. So there is a sequence with more clouds, and our decomposition doesn't deal well with that right now. And of course, if we had other atmospheric effects like haze or fog, we would also have problems. So we'd like to deal with that to make it more robust. And then I think we could use this technique for more robust background models in computer vision, in particular for applications in surveillance. I think there's actually a cool thing that one could do with virtual Earth and integrating these kind of illumination changes into something like virtual Earth, so that you might be able to simulate how the sun or whatever changes, the illumination changes in things like virtual Earth. And you could also possibly play back those videos and use them inside those different virtual worlds. So there's different applications in relighting, surveillance, and ultimately also I think this could be used for some kind of video compression. And just lastly, acknowledging the SIGGRAPH reviewers, Jason for giving us help with his code, and then those people who graciously shared their data. All of the videos you've seen were straight from the web, from usually webcam, so pretty low quality video. And Simon is supported by the NSF. Thanks a lot.
We have time for 1 or 2 questions.
Yeah.
So I have a question for the version scene.
Right.
What's the difference between the sun and the sky images?
Well, I mean, actually, so we made the observation. We first thought that we have to decompose the scene into more components because of specularities. And it turns out in these scenes, because everything is so far away, it's pretty much Lambertian. Even windows, they basically reflect the environment, and it's hard to tell if you're seeing a tree or if you're seeing a reflection of a tree in these videos. So it's basically treating it as if it were the tree. So in other words, all of the scene points are pretty much Lambertian, or pretty much diffuse, and with exceptions, of course. So that's already the case. And so what you're seeing here is really the decomposition that you get.
Why do you need 2 images?
Well, you do want to separate between the skylight and the sunlight because there is a very strong color difference between the two, as you could tell. I mean, and also looking at those, pixel intensity curves, you saw that whenever the point was in sunlight, there was a big jump in the intensities. Yeah.
You have this position, which is essentially just an outer product of 2 1D vectors, right?
Yes.
So do you take advantage of that you actually have this one rank decomposition of the matrix.
Advantage in what sense you mean?
Well, you know, like you try like maybe using an SVD to decompose, because I mean you know that you're looking at the one rank decomposition.
Right.
Matrix, right?
Yeah.
So I'm wondering if there's any advantage to be gained by that.
Yeah, I don't know. We haven't thought about that actually. So possibly we should talk more. Yeah.
I think an issue is that when the real-world illumination doesn't map directly to your measured illumination, the illumination clips in the camera or drops below a shadow level, or the camera is doing dynamic range compression or even just automatic exposure adjustment.
Right.
So real-world intensity doesn't match the data you're actually
right. So these cameras probably had auto exposure adjustment. We're not sure, but we assume they did because we can observe that the intensities do change over the time. So we can deal with that. But you're right, whenever we have glare, or in the Tokyo sequence there was actually a strong glare of the sun shining into the window that was just in front of the camera. And so basically what we do is we remove those frames. Typically it happens for 10-15 minutes, and we just remove those 2-3 frames out of the sequence. But you're right, we can't really deal with very strong illumination changes such as reflections or glare.
But your model then is really more a model of the measured scene as opposed to the real scene.
Yes, that's true. Absolutely. Yeah.
So I must say I'm also a little bit amazed that you need 2 RGB images, because and these curves of the skylight and of the sun, are they simply intensity or are they RGB curves?
They're RGB curves.
I see. Because if you think about it, the building itself only has one color, right? Which is eliminated or multiplied by the illumination component,
right,
of the sun and the skylight.
But remember, the final decomposition, we add those 2 components together, right? So it's an addition at the end. So that gives you the final color.
But how come, since there's only one color for the building, how come why do you need 2?
Because we observe the building under 2 different illuminations. We do observe it when it's in shadow, and we do observe it when it's in sunlight.
But isn't there an underlying model that says, in shadow it's going to be this, the color times the skylight plus the color times the sunlight, right? And so there's only one source RGB value there.
Right. I think the color actually relates much more to how the skylight and the sunlight changes. So it tells you more about the changes in the light than the changes in the surface. Of course those 2 are related, right? Because we're just observing. So of course we're observing the effects of both reflectance and illumination. But if you just look at those curves, they really seem to indicate most of that effect is due to the changes in illumination and not in reflectance. You're right, the reflectance changes, not. Doesn't change.
Let's take one more and then you want to come
You
to
mentioned surveillance as one of your applications. It seems, could you comment on how you would run this in a non-batch mode? It would seem to me that for maybe surveillance applications, you would use a factor on the previous day and use that mode for the first day or so.
Right, that's a very good idea. So yes, you can actually, the factorization is relatively fast, especially I think we can come up with an incremental version where we just add another frame and then do a new factorization. So we can do that. And of course the quality will improve as the day goes on. But then you're right, we could use the previous day's results as the first, the first decomposition that we use. So in other words, use that as a bootstrap. Yeah, we haven't done that. That's a good idea. Okay, thanks again.
Great. Thanks a lot.
Let's start on the first one. Okay, sorry about the technical difficulty. I'm not really for conspiracy theories, so I won't press the issue. I'm Frank Dellaert. I'm at the Georgia Institute of Technology, and I'll be talking about work that is primarily the work of students. Grant Schinder, who should be here, yes, he made it. Ming-Chuan Sun, who's also there, and this is joint work with Singbing from Microsoft Research. And this has been supported by Microsoft Research as well as an RFP proposal that I submitted to Microsoft and the National Science Foundation. And I'll talk about the 40 Cities project. Now, the primary students is Grant and Ming Xuan, and there's also a student that's now at Apple whose work I'll talk about as well. Of all the students that are listed here, in fact, these two are also at Microsoft Research interning, and he's at Microsoft Research Cambridge. So my whole group is basically gone. Very productive summer, because I don't have to talk to all these students every week, you know. But then you have these faculty summits, etc., to go to. Well, I'll talk about what the 40 Cities project is about. This is a picture from the 1920s of Atlanta. This is actually the Candor building. And it's remarkable in that it's, you know, this is the biggest building, the tallest building at that time. It's an early skyscraper, and it was the headquarters of the Coca-Cola company, so the first headquarters. In fact, on the other side there is this big Coca-Cola sign, which will pop up in the talk later as well. Now, when you fly over Atlanta today, you hardly see the Candor building. Okay, so this is a contemporary picture, color of the Candor building, and it's dwarfed by these skyscrapers, the Equitable and the Georgia Pacific building, and then there's the Westin there. And you know, you have to really know where the building is when you fly over Atlanta, or you can't see it. You know, just can't pick it out. So the 40 Cities project was premised on the fact, well, you know, let's assume that we can solve the 3D reconstruction problem. Okay, so wide baseline matching is a hard problem, and I'll talk about, you know, why it might still be harder if you enter time into the equation. But the premise of 40 cities is, suppose you have hundreds or thousands of photographs of a city over time, over 100 to 150 years. Can you reconstruct a 4D model of the city, i.e. a 3D model with a little time slider, so you can go from, in Atlanta's case, 1864 to 2007, and then possibly beyond. You know, that's future work, no pun intended. Atlanta is a great case, as I said yesterday in the at the faculty summit. Sherman, who was a Union general, came through Atlanta, and I have these beautiful pictures. There's a couple, like 10 or 15, from the Library of Congress, of a photographer that came right after Sherman came. Okay, in fact, he came with the troops, took a number of photographs, and then he took a number of photographs after Sherman left, and basically most of the buildings in Atlanta are leveled by Sherman in 1864. So you really start almost from scratch in Atlanta, and then, you know, you go all the way to now, and it's a metropolis of 5.4 million people now. Right? So why are we doing this? Well, there's a lot of interesting applications, right? So pushing the slider beyond 2007, this is a growing metropolis, 5.4 million people. You would like to know what happens with urban sprawl, what the dynamic of a city is. So there's some very interesting questions there. I very much like the historic aspect of it. I love looking at these pictures from 1864 and seeing where they were taken, exactly in what context. And so that opens the possibility of you know, doing tourism in time. Take your favorite city, be it Seattle or New York or San Francisco. San Francisco has this interesting resetting as well, right? With the earthquake in, was it 1916? Or 1906, right? And there's these beautiful books from San Francisco before and after the earthquake. And it's just fascinating to watch them, you know. And can you imagine seeing or doing this on your computer, and just with the interaction that is afforded by programs like Photosynth or Sea-Dragon, the zooming in scale and resolution and space and time, being able to visit a city throughout its existence, okay, which is very cool. Now, we can only do this at this moment from the beginning of photography, which is around, I guess the 1850s to now. And interesting future work would be also, well, can we do this with painting? So there's some really cool, almost photorealistic paintings from Venice that you could almost regard as photographs, and can you work from those? There is obviously that's a great way to educate kids about the history of their location, and as I said, like a 4D photosynth would be a fantastic thing to have. Now we use imagery. We have a sort of partnership with the Atlanta History Center, being very close. So an interesting anecdote is that I submitted this idea to the National Science Foundation multiple times, okay? And I submitted it multiple times because they rejected it multiple times, because I kept calling it 4D Atlanta. And one year I got wise and I said, well, I called it spatio-temporal reconstruction of urban environments with applications in digital archives. And they funded it right away. So I guess they didn't like the Atlanta part. But Atlanta is very close. We have this cozy relationship with the Atlanta History Center, so we get all these pictures scanned from their archives, and we took our own pictures. So that's conventional digital photography. It's quite interesting that talking about wide baseline matching and 3D reconstruction, some nasty things happen if you work on the scale of tens or decades, right? So this sign, which is this sign, it's physically the same sign. Okay, so this was in front of the Coca-Cola headquarters, but then when it ceased being the Coca-Cola headquarters, they physically moved the sign 300 meters or 300 yards down the road. Okay, so appearance-based matching has to be followed by a robust outlier rejection to deal with these things. Of course, the photometric quality of images can be vastly different. I mean, you can take 10 megapixel images with your Nikon D200 now, or you can take crappy video with your small video camera and get images like that, and then compare them with scanned large black and white images from 1910, say, and this building here is the same as this building. This is Atlanta's version of the the Flatiron building, which was there before the New York version, by the way. But here it looks white, and here it looks dark. So I very much like thinking about photometry and how light and changes and the imaging technologies change the images, and how to reason about that, right? So I'd love to talk with you because it's very cool thinking about all these things. We also have video shot for promotional video. So I have in my office 10 stacks of 35 millimeter film that waits to be digitized, and this is a snippet of it where Atlanta was promoting itself to be the site for the 1996 Olympics. So we have this fantastic footage that we could use for 3D reconstruction and view-based rendering. And recently I myself got up with a little plane and shot some with Irfan's camera, which I nearly dropped out of the window. We also went out and did what everybody seems to be doing these days, is take a truck, take some laser rangefinders, put them transversely, so as you move the truck forward, you get these laser range scans, and we took them through an urban corridor in Atlanta. An interesting fact about GPS in urban corridors is that it doesn't work. All right, so these traces here are the GPS traces of our two runs, and it's completely unreliable. So we also put a laser rangefinder that looked forward, so we can do scan matching to try and get a better odometry on the truck, right? And we took high resolution imagery while doing that. And a student of mine made a reconstruction of it, very preliminary, We haven't really done anything with it since, simply lack of manpower, but we have this laser data, 2006 laser data, right? Now, which could be used as a reference 3D model for building the past on top of it. All right, so let me now talk about 3 vignettes of things that we tried on getting a handle on this problem. So I'm not going to talk about 3D reconstruction or wide baseline matching because a lot of people are working on that, and we want to use their work rather than make new inroads in that area. But we did ask ourselves the one question, which is, well, suppose you have an image from an urban environment. Where was this picture roughly taken? So you could think of this as the Flickr question. So here's on Flickr you can tag your images with tags, and so maybe somebody tags their images with, well, here's the Canner building and the GP building. Okay, so if you only had those tags, could we then actually figure out where this picture could have been taken from? So very poor information. Simply somebody looking at the image and say, well, yeah, that's a Canner building and that's a GP building. I recognize those. And of course, we want to replace that by a machine learning algorithm that then automatically does that, right? And to make inroads in that, we just assume the existence of an existing rough 4D model. So here's a 4D model. In the beginning, there was only the Canner building. And then as time goes by, more and more skyscrapers appear. And we by hand modeled about 20 buildings in Atlanta that way. Okay. So here's some top views, and here are some of the images that we used to roughly model those. And so these are the images placed in context in that rough model. That's already cool, you know, just to figure out where all these images were taken over time. We find out that a lot of them are taken at the same spot throughout the years, you know, on the tallest building in town. So everybody goes up there, takes the elevator, and starts, you know, taking photographs. So it's an interesting witness to history. 3D reconstruction and structure from motion. As I said, you could use machine learning techniques. So here we just looked at the distribution of SIFT descriptors, a histogram of SIFT descriptors, to see whether we could distinguish between 3 buildings. This was just a one semester project of a student, a master's student that worked with me, where green is the equitable, blue is the GP building, and then this red is the Canner building, and the RGB values indicate the posterior probabilities of these buildings. So it does a reasonable job, I guess, but you know, this could be pushed much more, right? But in in the trend that people will tag it for us, let's take an image here and just assume that somebody tagged it for us with the building names. What we then do is actually sample the space of all possible viewing directions and viewing translations and come up with hypotheses that then could be checked using Ransack or some matching technique for whether it's the correct viewing location. And the way to do that, well, we took a page from the graphics people and used binary space partition trees to figure out, if you give me a couple of tags, well, we just took the whole space, divided it into voxels, and for each voxel calculated, can you see both these 3 buildings from this place? And you get these cones of visibility, not surprisingly, right? Where everything that is in the shadow of certain buildings is just impossible to have the photo taken there. And then from what is left, we sample the most probable locations. And so I can go into the technical details, but I won't. Suffice to say that this is a mixture density where you could be on the ground. That's the most likely probability. You could be on the surface of another building, looking outside a window and taking a picture. Or there's very small probability that you're in a plane somewhere and taking a picture. Right? And when we apply this to actual, so this is raw from Flickr. We actually took some images from Flickr. We didn't touch the tags. They were user supplied. We didn't know the user. Here are some of the results. So, so we get pretty nice hypotheses as to where this picture could have been taken from. I should explain that these are the synthetic views that we render from that hypothesized position and viewing direction. So this could be pushed much further. Unfortunately, the student went and worked for Apple, and he's very happy there. And so, if you want to send me some interns in fall, be happy to take them. Next, and I think this is the most successful nugget thus far is some work that Grant Schindler did on figuring out, well, if you have a set of images, so here is an example with 6 images, what order were these images taken in? Suppose I don't give you the dates. Can you figure out at least a temporal order? To computer vision algorithm, 1906 doesn't mean anything, but the order in which images were taken could definitely be something it could figure out, right? And we will assume here that 3D reconstruction is solved. So we did this Y-baseline matching, and structure from motion works by establishing a set of correspondences and then solving a large optimization problem, which gives you both the location of the points and the location of the cameras. Okay, so I'm kind of assuming that this is known in this audience. Now, if you have a 3D reconstruction, so here it's faintly visible, but here is all the yellow points. We can reproject them in the source images and label them in 3 ways. In fact, if it doesn't reproject, we will call this a white point. Okay, so it's not supposed to be seen in this image because we know the viewing cone, we know the 3D, so we can label it. Well, this is kind of agnostic. The common case is that we reproject a point in the image, and it is indeed one of the features that we use in our 3D reconstruction. Hence, it's an observed feature in this image. Okay, and the third case, which is an interesting case, is, well, it should be there, but it isn't there. Okay, now why could that be? Yeah. There is no building yet. In this picture, that skyscraper, which is now we know to be there, is not there. Okay, so so that's one hypothesis. It could be that the building is not there yet, and of course, there is this other hypothesis, which is the building's been demolished. Okay, which also happens. So there's a beautiful hotel in Atlanta that they demolished and put this big black thing in between in its place. So good. So we could do this for all the source images. Okay, and here is a graphic from Grant where he did this, and you can then collect all these visibility bits really in a matrix, which shows the columns are the images and the 3D points are the rows. Right, so in a random order here, right, where again blue is observed, red it's missing somehow, and white, it shouldn't be observed. I mean, we know it's out of view. And now we could actually figure out the order of the images by realizing that this is a constraint satisfaction problem. What we want, okay, is that a building is not there because it's not been built yet. It's there for a while because it was built and it exists, and then it's demolished. Okay, but what we will not have, okay, is this blue, red, blue, meaning it exists, then it is demolished for a while, and then it exists again. Okay, now it seems that in China, for the Olympics, they're actually demolishing some buildings and putting exact replicas in their places for something to do with Olympics and some restoration or something. So if we catch some images in the exact moment between those two events, we will be in trouble. Okay, so it's an assumption, but rarely violated in practice, and it might not work in China. So you could solve constraint satisfaction problems using a technique called backtracking, which you probably all remember from your early AI courses. Or you could use these little random swaps. It's almost like Markov chain Monte Carlo, which is why I like it. Which is, if you take the 8-queen problem, right, you have to put 8 queens on a chessboard such that they can't capture each other. One of the most efficient ways to solve that constraint satisfaction problem is to simply swap, do small little twiddles to the state space to get to the solution. And so it turns out that that technique of local search, simply doing swaps between images, works quite well in this case. Okay, let me show you, actually, before I show you this, here's an animation, beautiful animation made by Grant here, where he swaps the location of images randomly, and when it seems to be a good thing, he keeps that swap, and otherwise he just discards that proposal. And the matrix in between is reordered in a nice way. Now, going back to the previous slides, sometimes when pictures are taken at exactly the same, these errors should be, I think, about these. I don't know. At the same time, we cannot actually distinguish their relative order. So what we get is a partial order. And constraint satisfaction will simply exit the moment a partial order is reached, right? Which satisfies all constraints. And similarly here. And of course, and the animation already gave it away, but our algorithm doesn't use anything about time progressing in a forwardly manner. And so the opposite solution, where time is simply reversed, is also always a possibility. And we hope that, by just checking where color appears, we might be able to distinguish that. Then, as a total afterthought, because we hadn't really foreseen this, it turns out that we could also reorder the rows of this matrix. And we saw that several of these rows have the same pattern, blue throughout, or here this here seems to be not existing, then existing, and then being gone at the same time. That was interesting because it allowed us, by grouping these rows and then taking the convex hull of the 3D points, we automatically got a segmentation of the 3D points into buildings. And yeah, so that was kind of cool after the factorization, so here's a total overview of the algorithm. Here is the 3D reconstruction. We look at all the projections. Everything drops into this matrix. We do the local swapping for constraint satisfaction. Then we swap the rows and group the rows, build the convex hulls. And then what we can do is actually go at a single viewpoint and render the view from that viewpoint over time as new buildings come in, right? With conventional rendering, which in this case we botched a little bit on that texture. Okay, so that is that. The last part is something, and I'm going to be very quick about it, and we haven't really pushed on it as much as we can yet, which is, well, suppose you have a 4D model now. How do you realize a 4D photosynth? i.e., how do you render an image from any given point in space, any viewing direction, and any point in time? And so this is not it's fairly straightforward, but it's not a straightforward texture mapping operation. So here's a sequence where we just used view-dependent texture mapping. Okay, and it looks okay and looks cool. I also want to show you the underlying 3D points here, which will appear in a minute. So here are some underlying points that we use to solidify the 3D reconstruction. And by actually a trick which I think is due to Noah actually, by taking the 3D structure and then morphing it into the source images, you get this very cool video where you see where the transitions between viewpoints and time at the same time. So this is an old texture in a new photograph. Sometimes you get these artifacts of occlusion, right? So we are also thinking about, and I'm going to be quick about it because I've been told I only have 2 minutes left. But the question is, we have a 4D model, we choose a viewpoint, we choose a time, we have some source images, how do you render that image? And it comes down to figuring out, well, given that chosen viewpoint and that chosen time, which pixels in the source images can actually contribute. And the ones that can contribute are the ones, obviously, that are visible from the viewpoint. So that's simply 3D. So if you figure out whether this thing is visible or not, so you need a 3D model. Or the other thing is that the building has to exist at that time. So you have to reason a little bit about time and 4D models to figure out these mappings. And if you do that, then you can compute these weight maps, which allow you to, and here's a little animation of this changing over time. Here's weight maps that are computed as time progresses. More and more pixels are taken from newer images and synthesized in the image at the bottom. Now this, we still haven't quite figured out exactly what to do with the sky and with things like trees and unmodeled entities, which are needed to make this kind of SIGGRAPH quality, because I understand that if you don't have a Hollywood-style movie, SIGGRAPH is very difficult. So we have to really get at how to do this really beautifully, and that's what we're pushing on, or what Michuan will be pushing on in the fall, actually. All right, so what's next? Next is not 4D cities, but 4D Earth, of course. So I'm going to stop there and take questions.
One or two. So the idea was that you can have a building, you can have a point that disappears and then reappears again. But what if it was just occluded by something new that came up and then got removed, like a tree, for example, or a new building?
Yeah, absolutely. So that's what Grant is pushing on now. So to actually scale this up to a large number of images and unmodeled structure, we have to somehow deal with occlusion. And it's a tricky problem because once occlusion is in there, and I talked to several people about that, it's a very, you have, say, 10,000 points, and all possible triangulations on these 10,000 points can give you all possible occlusion scenarios, right? And so all of a sudden you have an extremely large state space to deal with.
Just that, that point about points, being included. In earlier work you didn't show today, you had done something about vanishing lines, right? Extracting vanishing lines,
right,
which suggests you can actually get surfaces. Why did you decide to go point-based when you could have done something more at a surface level?
Yeah, that's right. And in fact, if you look at the underlying 3D structure where you have these beautiful surfaces, you could extract. So I think that's one way to push on constraining the number of possible occluding surfaces, right? And in fact, in other work, we're modeling much more, a little bit like facades, where we have these block-based models which give us occlusion at a much richer level than just points, right? Can give us. So that's right. So those are some of the ideas. Other ideas are more non-parametric because you impose a lot of structure by thinking about planes or boxes, and that might be desirable, might not be.
So we're going to have a break now. Is there anybody who has brought things and demos or something that they would like to just share with people during the break? They'd like to introduce for 20 seconds? No?
Yeah, well, I can show you the 1864 pictures.
Anyway, it'd be great. So if you have things, please talk to the speakers. There should be some new refreshments, I think. And we'll reconvene in about 45 minutes.